Hello and welcome to the next episode of Klingberg Wing Mark II Development. I'm Rob Klingberg, your host. It seems recently I picked up a lot of new subscribers on my most recent video, and I thank you very much for that. But it appears that we now have a number of people in our august group that are not familiar with all the things that have happened that have led to this point where I'm getting ready to test this new slotted flap concept. And I thought I'd make a little video here to bring them up to speed and maybe more clearly define what's going on and what I'm working on. And that said, I'm going to go back and we're going to review some fascinating flight video. You'll get to see me at my last flight at El Mirage, and we're going to go through that step by step and watch the problem occur and discuss why it's occurring. I'm going to reference you over to another video, and then I'm going to have a further discussion here using the whiteboard. And I thought it was a good thing to do while I'm waiting for the wind to pick up at the beach. Anyway, before we go look at that flight video, let me say to you that the reason I do this is both for my own personal desires, things I want to develop, a little bit of fun, something interesting to work on in my retirement. I also want to disseminate the information out to a wider audience. I had a person ask me once, why don't you publish in the AIAA papers or something like that? And I said, well, I actually want people to see the information. I want them to be able to use it in their designs or get ideas for their own designs. And it's in some published paper these days, it's just going to sit on a shelf somewhere and get dusty, is my fear. And really, in our current methods of communicating, this is how you do it. This is how you get data out to the widest variety of people possible. So I do this instead. I was trained to write AIAA papers, but now I do this instead because I think it's more effective. And that said, I do this out of my own desires. Nobody pays me to do this. I'm not working for a company to do this. So money comes out of my own pocket. And that said, I encourage you that if you find these videos helpful, if you think I'm doing a good thing, you find them useful, or you think it's useful for the aviation world in general, then I'd ask you to kindly go down into the description and click on the Buy Me a Coffee link, except it's Buy Me a Gallon. Go on over to my Buy Me a Coffee site and throw $5 in the pot for a gallon of gas. It takes a lot of gas to drive to the flying sites and back. If I go down to El Mirage and back, a couple $100. Going out today, that'll be a quick $50. So if you can help with the gas, you will directly support the work that I'm doing here. And I'd be eternally grateful. Every donation gets a personal note of thanks from me. If you're not financially liquid enough to do that, at least hit subscribe and give me a thumbs up that you like the work that I'm doing, because that helps my YouTube algorithm. So all of that said, let's spin you around and let's go over and walk through that last flight that I had at El Mirage. You're going to love the footage. First, a little intro here. We're looking at me sitting on the lake bed here. We're towing with my truck, and if you look closely at the right screen, you'll see my view going forward, so you can see the airspeed there, and you can see the tow line going out to the truck. You'll see that we're using a Y bridle, which wasn't working properly, which caused some of the problems. It's supposed to tow through the CG. We were actually essentially towing from the nose of the pilot's cage, which was causing a nose-up pitching moment. And that nose-up pitching moment I had to counter with down elevator, which is problematic for my glider. So anyway, you're going to watch a video that's a quarter speed, and I'm going to attempt to talk us through it as we go along. And here we go. And here we go. So you'll see that I'm holding down elevator, and I'm going to need that because the weight on the nose wheel is a little light, and I'm holding down elevator to help keep the nose on the ground. It's my only way of steering. You'll see that we're using a Y bridle to tow with. and watch the airspeed, watch that Y bridle. I'm going to pause this when I release so we can discuss the conditions of the glider at that point. And we're rolling along here. We start to see the airspeeds coming active. We're up to 10 miles an hour. And as we hit about 10, the flow improves on the main wing, but it's still going out span-wise along the elevon. If you follow the link in the video description, it explains how that flow can go straight back on the wing and then turn 90 degrees and go out to the wingtip. It's the most bizarre thing in the world. But it's all due to Reynolds number and the velocity of the aircraft. So I think we're up to about rotation speed here. We're up about 15 plus. Stall speed's 23 miles an hour. And I think you're going to see me rotate here shortly. As I rotate, the elevon comes back up and the flow starts to improve a little bit over the elevon, and I lift off. But then, because of the nose-up pitching moment from the Y bridle, I have to put in more down elevator. Then the flow separates even more, goes out along the tip. What we should have done at this point was really accelerated, gotten up to about 30 miles an hour, 35. It would have maybe have solved this problem, but it's probably a good thing that the problem was exposed. So I think we're coming up on release here, and I'll stop the video and we'll have another little chat here. So very soon. So there's the moment of release, and you'll see that I still have a fairly large amount of span-wise flow on the elevon. Not as bad as before out at the tip of the elevon. It's a little bit better. There are reasons for that, but I won't get into them here. And you'll see that despite my advanced age, I'm still pretty quick on the stick. And as soon as the release occurred, that nose-up pitching moment went away instantly, and the nose is going to drop on me because I don't have that nose-up pitching moment. So I rapidly feed in some up elevator, and that'll bring that elevon back up into a neutral position, and you'll see all the flow reattach. Happens in a matter of just... Okay, so keep your eye on the airspeed and the elevon there. It's up to neutral, flow's attached. I'm putting the nose back down again, back up, reattaches. Oh, starting to separate. Airspeed's down to 20, which is stall, and out of the sky I fall. So a very tricky situation that's hard to control because of the non-linear performance of the control surfaces. You just can't keep up with those changes. And this is probably the only time you'll ever see a flying wing ground loop. One of the wheels came off a rim and I went sliding around the lake bed. Okay, welcome back. So you saw how the flow separates off the elevon, and you'll find down in the description, you'll find a link to a video. It's kind of long, it's about an hour long, but I do the computational fluid dynamic analysis of what's going on in that airfoil when an elevon is deflected, and I begin to show where the problem's coming from. And it's coming from an area that I don't think anybody's ever really worked on before, and that is that pressure wall that occurs at the hinge line of a standard control surface. And I also discussed in that video why flat plate elevons appear to work in this particular case for these hang gliders. And I want to remind everybody, and many people didn't know this on the last video, we're talking about Reynolds numbers that are really low, down around 400,000. That is an extremely tricky area, and it's not widely studied. So all of the standard answers of it's this problem, it's that problem, you could use turbulators, you could do this, you could have a slat, and on and on and on. None of them work. And the reason they don't work is because all of those standard answers are for standard flight conditions, quote unquote standard, which are much higher Reynolds number, 1 million and up, where flow behaves completely differently. And the models that I built and other flying wing models work great because they're all down in the laminar flow region. They're below this 400,000. So I'm working in a region here, and most of our hang gliders fly in and out of this region where there's not a lot known about the aerodynamics. Now, you can go look at the hang gliding world and try to find data, and I wish you good luck at that because most hang gliders have been developed empirically. Make a small change, go out and test it. Oh, that worked. We're going to keep that. Oh, that sucked. It was horrible. We had a lot of drag, so let's not do that again. but nobody ever goes and really collects hard data in terms of the aerodynamics to find out what's going on and why. And I haven't seen a lot of numerical analysis of hang gliders. It's probably out there somewhere, but difficult to find. Plus, hang gliders don't have control surfaces on them. They use wing warping. So that's not necessarily applicable here in my case. So what I wanted to take you through here was some of the basics of what's going on from a different viewpoint. The computational fluid dynamics, obviously very technical, and I thought I'd take an approach at a non-technical answer so that more people could understand without having a math degree. So here, we have here the red outline here is my airfoil near my wingtip. And just if you're not familiar with this kind of stuff, the line from the furthest point forward to the furthest point aft, this black straight line called the chord line. It's the length of the airfoil, the characteristic length. The dashed line that I have up here, I've labeled that the mean camber line, and that's what that is. Now, on the NACA 23012, which is what this airfoil is, the mean camber line actually arcs up pretty quick here in front, then slowly comes back down. And one of its unique features is it gets back down to the chord line, and then it just kind of goes straight out the back. Now, it's not very pronounced, but that's actually some reflex in the airfoil. Most airfoils, this generic one here, they arc up and they arc back down until they meet the trailing edge. And this mean camber line is at an angle to the chord line. The chord line would be straight here, and it's at an angle to the chord line. And that gives us this kind of flow aft of the trailing edge. The flow is going down, what we call downwash. You'll see that on most aircraft that fly. If you go out at the airport on a foggy day, you'll actually get to see this flow behind the wing. And it's fascinating to watch it. This is typical, but for flying wings, we don't like that so much. The downwash causes the aircraft to pitch nose down. That's why we have a tail. Tail puts a down load on there and lifts the nose back up. This is all a result of generating lift. So what they do on the NACA 23000 series is that they have this slight bit of reflex here, and what that causes is it causes the flow, instead of going down at an angle, to go straight off the trailing edge like this for the most part. And that really reduces the nose down pitching moment. Plus, it's what we call front-loaded airfoil. They do a little dip here in the lower surface. I call it a dip. It's kind of flat here, and then it goes back down lower, and then it curves. And it's made up front causes the airfoil to be what we call front-loaded. The center of lift is further forward on these airfoils than most airfoils. And that helps hold the nose of the airfoil up, and the reflex helps push the nose of the airfoil up, and that gives this airfoil a nice neutral pitching moment curve, which we love for flying wings. And as a plus, cool airfoil, it can generate pretty high CL. And that's something that's often missing from a lot of flying wing airfoils. Symmetrical sections and so forth don't pull a lot of CL. And of course, that's what we want. We're flying a glider, we want high L over D. So it has the nice pitching moment curve and can pull a pretty darn high CL max. So a great airfoil. Now, at the trailing edge, I want to note here that the angle between the chord line and the surface is about 10 degrees. And that's going to be an important number here in a couple of minutes as I talk about this. Now, my elevon, this is the little cutout of it. This is from somewhere near the wingtip. This is the actual size and shape of the elevon. So it's hinged here about the center line, pitches up and down. Pretty normal elevon. Nothing unusual about that in any way. It's a ball and socket kind of joint. A little complex to build, but it's low drag, and when deflected generates a lot of lift. And we want both of those on our wing. But it caused problems. Here it is. We can view elevons as though the airfoil is not there. And you say, oh, if I just went and put this in the wind tunnel like this is the kind of flow that I would get around it. Here's the stagnation point. The flow goes up and around over the top, and the flow goes down on the bottom. And the lift is generally centered fairly close to the hinge point right here. which is about, in my case, is about an inch aft of where the seam is. Now, what we saw in the flight video is the flow begins to separate right about here, maybe an inch past the hinge line. And it just turns 90 degrees and goes out along the span. Horrible situation. And the video where I do the CFD analysis talks about why the flow is doing that, at least my speculation. There's not really any papers I could go look up. I don't think anybody's ever analyzed this problem before. So these are great for control surface because they generate quite a bit of lift. If you watch the CFD video and that analysis, you'll see that I end up with a flat plate solution. I'm showing that over here. And if we look at a flat plate without the airfoil in front of it, oh, the lift is generally right here, almost at the very leading edge of that flat plate. It's way, way, way up front. And in this particular case, that's a plus, because that's where the hinge line is going to be. We're going to hinge it right about that point, and the lift will be generated here, and essentially be hidden in the flow conditions here. So flat plate's not as effective though. This lift is much less than what we would get over here, and therefore less rolling or pitching moment available. However, that can be compensated for by just making the elevons a little larger or deflecting them a little bit more. So I'm going to provide another link to another video that shows me testing this flat plate solution on one of the sections of the wing. And we go from being able to deflect it, say, only 12 degrees before the flow separates, to as much as 24 degrees. Essentially a doubling of the amount of deflection. And why does that happen? Well, in the CFD analysis, I explain the technical aspects about why that happens, but I thought I'd take a shot here at showing you physically, visually, why that happens. So I'm going to get in the way of the picture here. I'm going to go over here and replace these streamlines here. So let's say that we have our flat plate here and it's deflected down this way, like that. Normally, in neutral flight, it'll just be going straight back right along the chord line. This is normally where the flat plate control surface would sit when you're flying along in neutral flight. So say we deflect it down this way. Well, because of this 10-degree angle that's here, kind of handy, you have 10 degrees here that you can go. You can go a whole 10 degrees and still be lined up with this upper surface. And that's kind of handy. And the best way for me to explain it, I have to invoke a little bit of mathematics here. When it's like this, oh, well, you're lined up with a free stream. When we're just flying along, the free stream's going this way, like this. I should probably get out of the way of that. And back here, the free stream is going this way, like this. Okay? So when the elevon is up here, it's lined up with the free stream. Very easy for this flow to turn the inside corner and go along the flat plate. And the lower surface, same thing, along the flat plate, because it's lining up with the free stream conditions, which is what it wants to do. The flow that's going over the airfoil wants to go back to the free stream conditions. So this flat plate actually helps it do that. Kind of handy. Now, in this particular case, we don't cause any discontinuities here until we exceed 10 degrees. With the elevon like this, and what you saw in the flight videos, as soon as you start to deflect this, we put a kink in the airfoil. What happens is, you get, let me just see if I can draw this in here like this. As soon as we deflect it, it's down here like this. Any motion that you make puts a discontinuity right here where you turn the corner. And by discontinuity, I mean discontinuity mathematically. And what this is, when you deflect the control surface and you have this discontinuity, that means that the first derivative that describes this shape, the airfoil shape and going around the corner, is discontinuous. And anytime you have flow conditions, whether it be aerodynamics, water, electricity even, if you have electricity on the surface, a charge on the surface, and it's moving along the surface, if it hits a discontinuity like that, bad things happen. Same thing with aerodynamics. The flow's got to get around that corner. It takes energy to get around that corner. What I talked about in the CFD analysis is because we're at such a low Reynolds number, the flow doesn't have enough energy to get around that corner. It can't make the discontinuity. So with the flat plate back here, we have 10 degrees of throw available before we cause any discontinuity. We're not causing the flow to do anything weird. We're not asking it to do anything unusual mathematically until we have 10 degrees of deflection in that control surface. You're saying, oh, okay, Raul, then you're really not generating any lift here. And I said, well, maybe. Very little. But how do you actually get any control force out of that? Well, what's happening here is we're redirecting the free stream flow like this. We are essentially reflexing one way or the other the airflow. With the flat plate, as soon as you deflect it down or up, you're causing this free stream to change. And when that not free stream, this is actually the potential flow field. You change the potential flow field and you send it down or you send it up like that. And when you do that, as far as the whole airfoil is concerned, when it goes down, the airfoil has more camber in it. That means this airfoil is generating more lift. More lift here causing a rolling or a pitching moment. And if I deflect it up, I'm uncambering or reflexing the airfoil, and that's going to cause a loss of lift on this airfoil. So it's not so much the lift that we generate on the Elevon, which is what the case was here. Of course, this guy does double duty. When you deflect him, you get lift off of this surface, but you also change the lift of the airfoil. And when you change the lift of the airfoil, you get much more rolling moment. So that's another reason why these are a little less effective. However, this avoids the problem of creating that discontinuity there, and you can get 10 degrees of deflection to do control of the aircraft before you start to have a discontinuity show up. So the first 10 degrees, in my mind, you get free. You're not mucking up the flow for the first 10 degrees, and then I get about another 12 before the standard separation kicks in, because as you go past the 10 degrees, you start generating some lift here, you cause that little spike in the pressure, and once again, you're back to, once I start causing that discontinuity, I'm only good for about another 12 degrees. So it's really the same answer. It's not like there wasn't magic here that all of a sudden, a flat plate can go to a much higher angle of attack. It can't. It can go at about 12 degrees, same as this guy. This guy gets up about 12 degrees and the flow separates off. Same here, but you got 10 degrees for free up front. You're not causing any spike here in the pressure distribution. And if you're not understanding what I'm waving my hands at right now, you really need to go watch that CFD analysis. I know it's an hour long, skip certain parts, but to get a full grasp of what we're talking about here, you need to go look at that. So, and then there's been some questions on, gee, Raul, why don't you do what the MkII did, or do what Yonkers did with their slotted control surface, slotted flaps, or essentially it's this. Let me get rid of this stuff here, and people ask, hey, Raul, why don't you come out here and do what Mitchell did? You got a little airfoil down here, and you have a bracket that goes down to attach to it like this. Actually, it'd be like this, and up and down it goes, and that's your control surface. And it might be closer to the wing, it might be further away. The size of this gap matters. People do different size gaps for different reasons. Oh, interesting. Well, yeah, that was very effective on the MkII, very effective on all aircraft that it's put on. It's usually used on powered aircraft, and not on gliders. I think it's only been on one glider, that'd be the MkII. This gap here, when you ask the flow to go through this gap, a lot of drag. it accelerates the flow when it goes through this gap, which helps it stay attached to the control surface. Big plus. But you pay a price there with a lot of drag. On the Mitchell wing, not a big deal, because standard Regala wings around flying around at 4-to-1 glide ratio. Mitchell wing comes along and does 10 or 12. It's like, wow, you tripled the glide ratio. So you got some more drag. So what? You're still doing 3 times better than everybody else. If we're up around 30-to-1, which is where I want to be, and regular hang gliders are flying, like an Atos might do 20-to-1. Oh, this extra drag's a big deal, especially when you want to go fast. When you're flying slow like the Mitchell wing probably never went more than 45 miles an hour. Not as much of a problem, but the drag goes as the square of the velocity. When I go 100 miles an hour, that's a lot of added drag. Will I go 100 miles an hour? Maybe, someday, who knows. But even 60, 70, you're paying a big penalty on drag. So these guys are very effective, but very draggy. And we could look at it this way. We could come in here and say, oh, what if I put a beam on here that goes back here? I cannot draw straight. I have shaky hands. And I put my little airfoil back here. I hinge it there. So I give it an extra moment arm and I put it way back there. And I generate lift back there and I cause the airfoil to pitch up and down. Well, this isn't as effective as a flat plate. This would just be a pair of tubes, a pair of pieces, 2 pieces of tubing going aft with a flap going like this. And you're like, well, that's not as effective because the flow here, the potential flow field will want to go up in this gap or go down. You're going to get a lot of turbulence in here. It might be fairly straight, but you're not reshaping the potential flow field this way. You're just generating lift and drag back here, up and down. So not as effective. We'd really want to reshape the potential flow field, which is what we do with regular control surfaces. That reshapes the potential flow field. The flat plate avoids the problem of the discontinuity for up to 10 degrees at the trailing edge here. So we get 10 degrees of throw available for reshaping that potential flow field, for reflexing the airfoil both up and down. And we get some control effectiveness that way. And we can go another 12 degrees, go up to 22, 24 degrees, and get a lot of control out of a control surface that is not as efficient. This is not as efficient as this. But if this can only go 12 degrees and this can go 24, well, I'm much better off over here. It's aerodynamically less efficient, but in the long run, it's a much more efficient control surface. So that's kind of what's happening here. And let's see, what other questions do people ask about this? Well, people asked about turbulators and all that other stuff, and I think I mentioned that they don't work because we're down at this really low Reynolds number. You start, there's no energy, there's not enough energy in the free stream to pull it down into the boundary layer and keep the boundary layer attached. So we have an interesting solution here with these flat plate control surfaces, which have been used in the past. I've used them, that were arrived at empirically. Nobody ever really thought their way through this, reasoned it out, and tested it to see, does it work and why does it work? And this is part of the reason why. And now, later today, it looks like the wind's coming up. I'm going to go out and test that slotted flap that you probably saw in my previous video. And I'll have the results up on Patreon, provided the wind holds out. And good, bad, or indifferent, the results will be up there. And let's see, what else do I need to cover here? I think I've covered it all. It certainly doesn't explain the whole story, but it explains why, it helps explain why I'm doing what I'm doing the way that I'm doing it. So as we get down to the end here, I know there's hardly anybody left. That's kind of how these videos work. There's probably 20% of you left that started out at the beginning, and I appreciate you sticking with me to the end. If you want the test results, please go over to Patreon, take a subscription there. If you just want to support in the near term, that too, you'll just go buy me a cup, click the link on buy me a cup of coffee, and put in a one-time donation there. It'll go directly to gasoline for getting me to the test sites. And please hit like and subscribe. Every penny helps. and it keeps me going to get this work done. I really appreciate any support you can give. If you go over to Patreon, that's the best deal, because I got a goodies package that goes out to every new subscriber. You get the flight simulator. You can actually fly this glider, minus the flow separation. You can fly my glider on your computer, and that's included in the welcome package. You get plans for the quarter scale RC model. You get a list of materials. You get access to whatever SolidWorks 3D modeling drawings that I've done. You get access to those. So it's a lot of wonderful benefits that come from being a patron. And you get to ask me questions directly that I'll take my time to answer efficiently and hopefully correctly. So I highly encourage you to go look at Patreon and give that a thought, or just buy me a cup, buy me a gallon of gas, and keep me going. And until we meet next time, I'm going to head off to the beach here, so I will say fly safe and bye for now.